By the end of this video, you're going to be breezing through these integration by parts problems, and in about 30 seconds, here's how this video is going to get you there. We'll be going through 4 problems in this video, and they'll be getting harder as we go. In the first problem, we're only going to have to integrate by parts once, but in the second problem, we'll have to integrate by parts twice. And in the third problem, I'll give you an example of integration by parts where we have a definite integral. And then in the last problem, we'll go through a special case of integration by parts where we have to integrate by parts twice and then add an integral to the other side. It's pretty weird, but we'll get it done. Now, I think the hardest part of integration by parts for literally all of us is choosing which function is going to be your u. And that's why in the last section for this video, I'm going to give you an acronym that's going to cut out all of that work. And we're going to use that acronym to find our u and our dv for all of these integrals. And then after we do all that, I'll give you a problem to try and answer it in the comments. And by that point, it should honestly be breezy. Lastly, if you're looking for the notes for this video, I took all my notes from this video and all my other videos on techniques of integration, and I made them into a workbook for you guys. To be honest, arts and crafts have never been a strong suit of mine, so I am stoked that I was actually able to make this. So yeah, the link to this workbook is in the description, and now let's get into this video. So starting off with this first problem, we have the integral of x times cosine of x dx. Now for this integral, or for any other integral, your first thought shouldn't be integration by parts. Your first thought should be, can I use reverse power rule on it, or can I do a u-substitution? For this integral, we can't do either of those things. We can't use reverse power rule. There's no u-substitution that we can do that'll make this integral simpler, and so we have to turn to something else, and that's where integration by parts comes in. Now this is the formula for integration by parts, and integration by parts is essentially the reverse of product rule. With product rule, we were taking a derivative of two things that were being multiplied together. And what we would get there is u prime v plus v prime u. With integration by parts, we're doing the opposite. Instead of taking the derivative of two things that are being multiplied together, we're going to be taking the integral of two things that are being multiplied together. Now, if you want to know where this integration by parts formula actually comes from, I have a quick video where I go through and derive it using product rule. I'll link that video on the screen and in the description if you're interested in that. So yeah, the idea with integration by parts is that we're integrating two things that are being multiplied together. And that's exactly what we have going on here with the x being multiplied by the cosine of x. Now, what integration by parts does is it turns this integral of u dv, of those two things being multiplied together, into this expression that has an integral that will hopefully be simpler than what you started with, the integral of v du. And that integral is only going to be simpler if you choose the right u and the right dv. One of these things in the integral, either the x or the cosine of x, is going to be your u, and then the other one will be your dv. And if you don't choose the right u, you'll make the problem harder for yourself. So how do you do that? Well, let's talk about that. What I'm going to do is I'm going to show you what the right u is right off the bat. The correct u for this problem would be x. And then dv, that's the other part of this integral. And the other part of the integral here is cosine of x dx. So that would be your dv. Then after we do this entire problem, I will show you what happens if you do not pick the right u, and what happens if you make your u cosine of x instead. And that'll help you sort out how to pick the right u in the first place. So like I said here, u is x, and dv is cosine of x dx. And for us to be able to use this equation, we have to find our other pieces, that being du and v. Now since u is equal to x, du is going to be the derivative of x, which is 1, times dx. And then v is the integral of dv. dv is cosine of x dx, and if we integrate that, we get sine of x. And so now we have everything that we need to plug into our integration by parts formula. Plugging in, we get that this integral is equal to u times v, which is x times sine of x, minus the integral of v du. Now v is sine of x, and du is 1 times dx. So v du is just sine of x dx. And now you can see that since we picked the correct u, which we'll talk about how to do in a second, this integral has been drastically simplified. This is an integral we can actually do. So we get that this is equal to x times sine of x minus, what is the integral of sine of x? The integral of sine is negative cosine. Okay, and make sure you're careful with your negatives here. Or we have a negative that comes from this negative outside the integral, and this other negative comes from the fact that the integral of sine is negative. So don't miss out on one of those. So we get our final answer is x times sine of x. We have two negatives, so that's a positive cosine of x. And then we have plus c. And that's our answer for problem 1. So while that is our answer, we still have to talk about this u and dv thing. How are we supposed to know that u needed to be x? Well, if we look at the formula again, it will tell you everything that you need to know. Du is what ends up in this simplified integral, and that's the derivative of u. So we want that derivative of u to be simpler than u. So when we are trying to figure out which of these two, x and cosine x, are going to be our u, the question is, which of these can we take the derivative of, and that derivative will be simpler? If we take the derivative of cosine of x, we'd get negative sine of x. And that's definitely not simpler than cosine, right? It's still a trig function. But if we take the derivative of x, that's 1. And I'd say a constant is much simpler than an x. So if we have u be our x, then we get du to be simpler. It's 1. And the other piece, the cosine of x dx, that's now going to be our dv. And that means that we integrate it to get v, and that's the other piece of this simplified integral, v. And if we integrate cosine of x, we get sine of x. And this simplified integral is these two things multiplied together. That's why we get sine of x. So again, how do you pick your u? Well, generally it's which of these can you take the derivative of and have that derivative be something simpler. All right, so now let's move on to problem 2. Now problem 2 is the integral of x squared times e to the x dx. And again, the first thing you want to do here is not integration by parts, but it's think, can you use reverse power rule here or a u-substitution? And in this case, we're not able to do that. So we have to use something else, and that's where integration by parts comes in. We see that we have the integral of two things being multiplied together, and we're like, oh, yeah, integration by parts. Now, the first question that you have to ask is, which of these is going to be our u, and which will be our dv? And so which of these can we take the derivative of and get something simpler? Well, if you take the derivative of e to the x, you're not getting anything simpler, right? The derivative of e to the x is e to the x, and that just keeps happening. But the derivative of x squared is 2x. And I'd say that that's definitely simpler, right? You go from a quadratic term down to an x, that's a linear term. So let's let u be x squared, and dv, that's the other part of the integral, that's e to the x dx. Now, du, that is the derivative of x squared, which is 2x, times dx. And v, that is the integral of e to the x dx, and that's e to the x. So now we have what we need to plug into the integration by parts formula. When we do that, we get that this integral is equal to u times v, which is x squared times e to the x, minus the integral of v du, which is e to the x times 2x dx. And I'm going to write that as 2x times e to the x dx. It just looks a lot nicer that way. So now we wind up with an issue here. This integral, it still isn't able to be integrated with reverse power rule or with a u-substitution. And so what we have to do is integrate by parts again. And if we want to integrate by parts again, then what's going to be our u? Well, if we take the derivative of 2x, if we let 2x be our u, the derivative of 2x, that's 2. And that's a constant. And that's going to be really nice. And then remember the other piece of that integral? That's the v. That's going to be the integral of e to the x dx, which is e to the x. So you're going to see here that below, in our integral, we're going to have 2 times e to the x. And that is something that we're going to be able to integrate. So this will be the last time we have to do integration by parts. So again, u is going to be 2x, dv is e to the x dx. So du, that's going to be the derivative of 2x, which is 2 times dx. And then we have v, that's the integral of e to the x dx, which is e to the x. So again, let's plug into our integration by parts formula. We get that this integral is equal to x squared times e to the x minus, okay, now here's where we're doing the integration by parts. We're doing integration by parts for this integral here. And that's going to equal u times v, which is 2x times e to the x, minus the integral of v du, and that is e to the x times 2 dx. And I'll write that as 2 e to the x dx. Okay, cool. So if we first distribute through this negative, because I don't like seeing these brackets here, we get x squared e to the x minus 2x e to the x. And then distributing the negative through to this integral here, that'll become positive. So we get plus the integral of 2 e to the x dx. And what is the integral of 2 e to the x dx? Well, this is the same exact thing as 2 times the integral of e to the x dx, or you can pull that 2 out, and we know the integral of e to the x dx, like we've been saying multiple times in this problem, is e to the x. So this will give us 2 times e to the x. So let's write that all out now. We get x squared times e to the x minus 2x e to the x plus the integral of 2 e to the x dx, which is 2 times e to the x. And then we have to remember our plus c. And if you want to clean up this answer, you can. You can see that all of these terms have an e to the x in it, so you can factor that out. And that gives you e to the x times x squared minus 2x plus 2. And you have plus c. So that's your answer for problem 2. So moving on to problem 3, now we're going to get into an example of integration by parts that involves a definite integral. So how does that change everything? Well, it doesn't really change things that much. All we have to do is this u times v, you just evaluate it from a to b, and then the integral that you end up getting, that simplified integral, that's going to have the same bounds as the integral that you started with. So really not much changes. So let's go through and do this problem here, and you'll see exactly what I mean. The first thing we need to do is figure out what's going to be our u and what's going to be our dv. And you might be like, all right, well, since in problem 1 we had an x and we had to integrate by parts once, and in problem 2 we had an x squared, so we had to integrate by parts twice, and in problem 3 then we have an x cubed, we need to integrate by parts 3 times, of course, right? Well, not quite. If we make our u natural log of x here instead of the x cubed, watch what happens. If u is natural log of x and dv is the other part of the integral, that's x cubed dx, then we get that our du, that's the derivative of natural log of x, that's 1 over x dx. And v is the integral of x cubed dx, that is x to the 4th over 4, or you can write that as 1/4 times x to the 4th, whatever you want to do. But as you can see here, when we take the derivative of natural log, the natural log part goes away. And so this integral here, this simplified integral, won't have any natural log in it. What once was a natural log is now just like a 1 over x, and that'll be in this integral now. And that's going to combine really nicely with the v, which is an x to the 4th over 4. And you'll see this in the acronym that we talk about later. Natural logs have this property, and also arctrig has this property. So something like the inverse tangent, you'd want this to be your u2 over something like an x cubed or an x squared, because when you take a derivative of arctan, you get 1 over 1 plus x squared. That whole arctan goes away. So it's drastically simplified. All right, so we know our u, our v, our du, our dv, we have everything that we need to plug into this formula. So let's go ahead. We get that this integral is equal to u times v, which is natural log of x times x to the 4th over 4. And that's going to be evaluated, remember to evaluate it, from 1 to 2. And then we have minus the integral from 1 to 2 of v, which is x to the 4th over 4, times du, which is 1 over x dx. Now this looks pretty messy, so let's clean it up a little bit. I'm not going to do this evaluation yet. I'll wait till we have everything integrated so we can do the evaluation all at once. And I'm going to write this thing a little bit nicer as x to the 4th times natural log of x over 4. And that'll be evaluated from 1 to 2. And then I have minus the integral from 1 to 2 of, well, I know that this x will cancel with one of the x's in the numerator, so I'll be left with an x cubed. And so I'll get a x cubed over 4 dx. So I can now integrate. And so after writing all this stuff in the front yet again, x to the 4th natural log of x all over 4, evaluated from 1 to 2. I can go through with this integration. I can first pull that 1/4 out of the integral. And then I can just worry about integrating the x cubed. The integral of x cubed is x to the 4th over 4. And that's going to be evaluated from 1 to 2 as well. So now let's go through and do that evaluation step. The first thing we're going to do is take this function right here and plug in 2 everywhere we see an x. So we have 2 to the 4th times natural log of 2 all over 4. And that's going to be minus this entire expression with a 1 plugged in. So that'll be 1 to the 4th times natural log of 1 all over 4. And I'm going to put brackets around that. Then we have minus this expression with a 2 plugged in, which will be a 2 to the 4th over 4 times 4, that's 16. And that'll be minus this expression with a 1 plugged in. So that'll give us a 1 to the 4th over 16. Now, continuing on here, 2 to the 4th power, that is 16. And 16 divided by 4 is 4. So we end up with a 4 times natural log of 2. And then we have minus, well, that looks disgusting. Let me fix that. There we go. We have minus, you see this natural log of 1 here? Natural log of 1 is 0. So this entire second term is 0. So we don't have to worry about that at all. So then let's talk about over here. We're going to have minus in brackets 2 to the 4th over 16. That's 16 over 16, which is just 1. But I'm going to keep it as 16 over 16 because this fraction over here is going to be a 1 over 16. So inside these brackets, we get a 16 over 16 minus a 1 over 16. And that's a 15 over 16. So our final answer here is going to be 4 times the natural log of 2 minus 15 over 16. And there isn't going to be any kind of plus c here because this is a definite integral. All right, now we're going to move on to the last problem for this video, problem 4. So for problem 4, we're asked to find the integral of e to the x times sine of x dx. And for this integral, which one of these is going to be our u? E to the x or sine of x? Well, which one gets simpler when we take a derivative of it? Does e to the x get simpler? Well, no, because if we take a derivative of e to the x, we just get e to the x. And what about sine? Well, if we take a derivative of sine, we get cosine. And cosine, that's not any simpler either. That's still a trig function. So neither of these functions seem to be getting simpler when we take derivatives of them. So what do? How do we find our u? Well, this is a special case of integration by parts, when you have an exponential and a trig function. And when you do that, you can actually make your u either e to the x or sine of x. The problem will still work out the same way. So what I'm going to do is I'm going to make our u sine of x. And the reason for that is because I'd rather have my u be the trig function, because I'd rather take a derivative of a trig function than integrate trig functions. So our u is sine of x, and that means that our dv is going to be e to the x dx. And now we can go find our du and our v. Now since u is sine of x, du is going to be the derivative of sine of x, which is cosine of x, times dx. And v is going to be the integral of dv. dv is e to the x dx. The integral of e to the x dx is e to the x. And now we can plug into our integration by parts formula. We get that this integral is equal to u times v, which is sine of x times e to the x, and I'll write that as e to the x sine of x. And that's going to be minus the integral of v du. v is e to the x, and du is cosine of x dx. So we get e to the x cosine of x dx. So now what do we do? Because this integral isn't any simpler than what we started with. We still have the integral of an exponential times a trig function. Well, all we have to do here is integrate by parts one more time. And we're going to make our u cosine of x. We're still going to make our u that trig function. And our dv will again be e to the x dx. Now from there we can find our du and our v. Our du, that's the derivative of cosine of x, that's going to be negative sine of x dx. And v is the integral of e to the x dx, which is e to the x. So now again, let's plug into that integration by parts formula. When we do that, we have this e to the x sine of x minus, and now here's where we're plugging into the integration by parts formula. We have u times v, which is e to the x times cosine of x, minus the integral of v du, which is e to the x times negative sine of x dx. So now let's clean this up a little bit, and then I'll be able to show you why we're even doing this in the first place. We get e to the x times sine of x minus, let's distribute this negative through. Distributing the negative through to the e to the x cosine x, we get minus e to the x cosine x. Distributing the minus through to the integral, it would make it positive because there's another negative there, but there's actually three negatives here. And so since there's three negatives, this is going to be minus the integral of e to the x sine x dx. So now it really looks like we did all of this for nothing because we ended up with the same exact integral that we started with. But that's precisely the point. We ended up with the same exact integral that we started with. And that allows us to do something really strange, but really nice at the same time. Again, what is this actually equal to? I haven't been writing what's on the left-hand side to save space, but it's that integral of e to the x times sine of x dx. Because we're trying to find what this integral is equal to. And now we have that integral on both sides here, and so let's get that all onto one side. Let's add this integral of e to the x sine x dx on both sides. When we do that, this goes away, and we have two integrals there, so that's going to be 2 times the integral of e to the x sine x dx. And that's equal to e to the x sine x minus e to the x cosine of x. And the only thing left to do, we're trying to find the value of the integral of e to the x sine x dx. Not 2 times the integral of e to the x sine x dx. So we just have to divide by 2 on both sides. And when we do that, we get that the integral of e to the x sine x dx is equal to e to the x times sine of x minus e to the x times cosine of x all over 2 plus c. And that is our answer for problem 4. Now again, this is a special case of integration by parts, and it's going to happen whenever you have the integral of an exponential times a trig function. Whenever you have that, the same case is going to happen where you have to add the integral to both sides and then divide off that constant. I know it seems a little weird, but you'll get through it. So yeah, that's problem 4. So now moving on to the last section for this video, I really want to nail home the point of how do you pick your U and how do you pick your DV. And there's a really great acronym for that, so you don't really have to think about this at all. And that's LIATE, or the cool kids pronounce it as LIATE. And by cool kids, I mean literally just myself. So this is an acronym that will help you find your U, and it's essentially a priority list. The first thing you'd want to pick for your U is logs. If you don't see any logs, then do inverse trig. If you don't see any of those, then do algebra. And by algebra, I mean like if you see like an x or an x squared or something like a x plus 3, all of those are what is considered to be algebra. And then if you don't see any of those 3, then you go to trig. And then lastly, you have exponentials. That's not exponents. So to practice finding our U, I have all of these examples here where we're going to go through and find our U and find our DV. And looking at some of these integrals here, they look pretty tough. And actually, I go through every single one of those integrals that you see on the screen now in the extended video for integration by parts, which I have linked in the description down below. So if you want to see the full solutions, you have that. But again, here we're just trying to find our U and our DV. Now, I'll underline our U with blue, and DV will be underlined in green. So starting with this first integral, we've got the integral of x times e to the 2x dx. Now for that integral, which one's going to be our U? Well, we have algebra and we have an exponential. And this acronym tells us that algebra is going to be our U before exponentials is. So x will be our U and e to the 2x dx will be our dv. So our first integral is already done. Now our second integral is x minus 1 times sine of pi x. And so that's algebra and trig. And since algebra comes before trig, x minus 1 will be our u, and sine of pi x dx will be our dv. Now what about this third example here? This one looks a little bit tricky. It's the integral of the natural log of square root of x dx. Now for this one, this is an example that you'll see with natural logs and with inverse trig, where it only looks like you have one function. All you're going to do there is you're going to picture this as being a 1 dx. And 1, you're going to consider that as being algebra. So in that case, your u is natural log of the square root of x, right? Because that's a log and that comes before algebra. And your dv will just be 1 dx, which is the dx there. And again, I have another example below of where we do the exact same thing with the integral from 0 to 1 of the inverse tangent of x dx. Again, you picture that dx as being 1 dx, and if you do that, you see that you have a inverse trig function, which comes before algebra. So your u is the inverse tangent of x, and your dv is dx. So yeah, I know it's a little weird, but it works. And again, I'm going to be going over the solutions for all of these integrals in the extended video for integration by parts, which I've linked in the description. But let's move on to this next integral here, the integral of e to the negative x times cosine of 2x. Now again, that's that special case that we did in problem 4, where we have the integral of an exponential times a trig function. And here it doesn't actually matter which you choose to be your u. It can be e to the negative x, it can be cosine of 2x. But I always like to take the derivative of the trig function rather than the integral of trig functions. That's just a little grosser, and a lot of people mess up with negative signs when you do that. So that's why in this acronym here, trig comes before exponentials. You'd rather make trig your u. So our u here will be cosine of 2x, and our dv will be e to the negative x dx. Now, we have a few more integrals to do here. We've got the integral of x squared times sine of 2x dx. So that gives us algebra and trig. Algebra comes first, so x squared will be our u, and sine of 2x dx will be our dv. And then in this integral below, we have x to the 4th times natural log of x squared. Natural logs come before algebra. So natural log of x squared will be our u, and our dv will be x to the 4th dx. And then we've got one more integral to do here. Again, it's the integral of an exponential times trig. It's that special case again where you're going to have to add that integral to the other side eventually. And here, trig comes first, so we make our u sine of 3x, and we make our dv e to the 2x dx. So that right there is how you pick your u. So hopefully you feel a lot more comfortable with integration by parts now, and if you're feeling pretty good with this, then here's a problem for you to try and answer in the comments. Here we have the integral from 0 to 1 of 1 plus x squared times e to the 2x dx. So try this problem out, let me know what your answer is in the comments, and if you have any questions on anything we talked about in this video, again, let me know in the comments and I'll try to get back to you when I can. Now remember, I do have that extra video where you and I will go through and solve 12 more of these problems with integration by parts, including some of the harder problems that I gave you at the end. It'll be some great practice, especially if you have a quiz or a test coming up on this kind of stuff. That video is linked in the description along with the workbook that I made for you guys that has all of my printable notes for all of my videos on techniques of integration. Lastly, make sure that you're subscribed to this YouTube channel, and thank you so much to those of you who already are. You guys are the reason why I've been able to do this full time since I graduated college. So yeah, that's gonna do it for this video, and I'll see you soon.